Okay. We will continue that our maximization lemma to find out the simultaneous confidence interval, this one. What I told you that this quantity, that A transpose x bar minus this one, if you select something like this for A, you will get like this, and which is basically like a univariate interval, and your problem will lie here that you will not get simultaneously 90% or 95% confidence interval. You will go, you require some modification, and that modification is given here by using maximization lemma, that z square n x bar minus mu transpose, and this quantity follows chi-square distribution. Now, with this modification you write the earlier equation. What have you written earlier? You have written A transpose x bar minus z alpha by 2, and this less than equal to this, less than equal to this. So, this z alpha by 2 will be replaced by square root of chi square p alpha. What sign? You see this one, A transpose x bar minus chi square of this square into this variability component, then A transpose mu less than equal to A transpose x bar plus the same thing. What is the problem? Paper also same thing I have written. This minus this less than equal to this, less than equal to this plus this. This is plus. Okay. So, what this change is like this, A transpose x bar minus root over chi square p alpha, then the same thing you write A transpose this divided by n less than equal to A transpose mu less than equal to A transpose x bar plus again you write that chi square p alpha, and same thing that A transpose this by n. Now, if you select A similar manner, then your individual confidence interval will be x bar minus chi square p alpha square root of again s j j by n less than equal to mu j, this will be mu j less than equal to x j bar plus chi square p alpha square root of s j j by n. This is the interval simultaneous confidence interval for x for mu j, simultaneous confidence interval for mu j, and if you change j equal to 1 to p, you will be getting for all other variables what is the confidence interval. Okay. It seems very difficult or easy. So, when you read that book, you read in this the approach what way I am presenting here, otherwise if you will find it very boring. At the first time when you see Johnson and Wichan, you will find that I will never read this book, and that is the purpose of this class, purpose that I am making it as simple as possible, so that you all feel reading that, please. Okay. So, now the three scenarios we have seen earlier. You tell me, are you facing problem here? Simultaneous confidence interval. Scenario 1, sigma is known. So, as sigma is known, you are using sigma jj, because if sigma is known, it is better to use that sigma. Why you will go for sample variance? If your sigma unknown and large sample size, you are using SJJ, you are also using chi-square distribution. when it is small with small sample size and Mn multivariate normal plus sigma unknown, you are using F distribution. Can you find out the confidence interval for the problem given? You develop. I am giving you 5 minutes time, although I know that 5 minutes time is very big for us, but you please develop. What I say that you have to develop simultaneous confidence interval for the mean of the variable x1 and x2 given alpha equal to 0.05. Everything is, the answer is with you. How do you go about it? Everything is given here. You see x1 bar is 10, x2 bar is 20 and your S11 is 40 and S22 is 100, and you require to know n minus 1 p by this quantity what will be the value. Earlier we have already seen that this quantity the critical value is 7.51. Just you put into this equation. So, 10 minus 7.51 that square root into square root of 40 by your n is 20, less than equal to mu 1 less than equal to 10 plus this quantity. Okay. I am sure that possible, and you see that these are the intervals. Which one? Whole square root, including f p n minus p alpha, there is whole square root. Okay. So, I think right hand side find out for x1 mu 1 and left hand side for mu 2. This side people find out for mu 1, left hand side please find it out for mu 2, cross check. x1 is okay, then x2 will also be okay. So, we will go to the next slide. I hope that you all will be, you have already found out the mu 1. So, mu 2 also it is possible, not a big issue. Then what is Bonferroni approach? Bonferroni approach is different than maximization lemma. Bonferroni approach says that our sole problem is when I have large number of variables, I am not getting this one. Now, this quantity definitely is less than 1 minus alpha, because alpha 1 minus alpha is always less than 1. So, what Bonferroni says that if we want to find out collectively 1 minus alpha into 100% confidence interval, so you tighten the individual intervals. You are getting me? Like my first variable individual interval, let it be 99% you are finding out. Then second variable also you find out the individual interval 99%. Then what will be the total? If you multiply 9.99 into 0.99, what will be this quantity? You just check. It will be also a large quantity. If my interest is to get 95.95, probably it is more than 0.95. So, you have to choose judiciously, so that ultimate this one, this 1 minus alpha to the power p can be like this. What I can say, it will be always like this, this should be greater than, that is my requirement. As a result, he has given a formula. He says that you can give equal weightage to each of the variables, or you can give differential weightage. So, let alpha is like this, my j is 1 to p, there are p variables, and I am giving each variable with alpha j weight, that will be alpha. What is happening here? So, you have suppose p variable x 1, x 2 to that x p variables are there. Now, this is alpha 1, alpha 2, you are giving probability value for each like this alpha p. Now, my question is this plus this plus this is alpha. If you give all variable equal weights, then this is your alpha p, then this will be alpha by p. Getting me? If you give equal weight to each of the variables, so there are p variables, your total should be alpha, you will be getting alpha by p. And what will be this alpha? That all depends on what is your 100 into 1 minus alpha percent confidence interval, and you have to check what I can say, you want to see this one. Okay. Now, let us see that using this for different scenario, what are the confidence interval. First one you take first. You see the first one, and you tell me whether you are comfortable or not. First one we have already seen that is z alpha by 2. Now, instead of z alpha by 2, you are writing z alpha j by 2, and here also z alpha j by 2. Now, if you give equal weightage, then this will be z alpha by 2 p, z alpha by 2 p, when your this condition satisfied. This condition satisfied, this will be z alpha by 2 p, this will also be z alpha by 2 p. So, here you are using z, here also you will be using z, but here your sigma is unknown, large sample size, your S will replace that sigma, absolutely no problem. Third one, instead of f, you are using T distribution. Okay. So, my request to you that chapter 5 of Johnson and Wilson you please go through and see that this derivation as well as whatever explanation given there, if there is any problem please report to me. Okay. Then what is essentially the difference between Bonferroni and this approach, maximization lemma? Which one is easier to you? Bonferroni? Easy way, you just divide the total alpha to different variables, collectively the sum will be alpha. Now, there is a problem. Example 4, consider the example 3, obtain simultaneous confidence interval for the mean. So, T n minus 1 alpha j by 2, that is 19.0125. How we have got 0.0125? Because our alpha is 0.05, then there are two variables, then alpha by 2 is 0.025, again the two tailed. So, further divided by 2, you are getting 0.0125. This value is this, and once you put into this equation all these values, you will be getting 6.45 less than equal to mu 1 less than equal to 13.55. So, I am writing this 6.45 less than equal to mu 1 less than equal to 13.55. Using maximization lemma, what was the interval we got? 6.12, 6.12 less than equal to mu 1 less than equal to 13.88. Okay, there is little difference. There is little difference, almost this one 6.12 mean this one is less than this one is more than this. So, little difference is there, that difference will always be there, because you are using different alpha values and different, here it is T distribution, there it is F distribution. Now, hypothesis testing, this is the last topic today. What is hypothesis? I told you in the last class, yes or no? That is yet to be proven. Any statement, and definitely it should be a good statement, it is not that I am going there, you are also going there, this type of statement, scientific statement. Any scientific statement that is yet to be proven, that is your hypothesis. And you have seen hypothesis in univariate case also. Now, in multivariate case, what will be your null hypothesis? When you are talking about single population, that related to mu we are talking about. So, mu equal to mu 0. What is my alternative hypothesis? Mu not equal to mu 0. Okay, very simple. What is this mu? This is mean vector. Please remember, whenever we are writing like this in multivariate domain, although we are writing mu, many a time you commit mistake. You think that okay, this is 1 mu, that scalar quantity, it is not like this. So, in hypothesis testing, the steps are find out the null hypothesis and alternative hypothesis, that is your step 1. What will be your step 2? What I have given you in univariate case? You have to find out the appropriate statistic. So, find out appropriate statistic. Then what will be your third step? You must know the sampling distribution, know sampling distribution of that statistic. Then what is the fourth step? You definitely compute the value of the statistic. From sampling distribution of the statistic, you find out the critical value. Then your step 5a, compare the computed statistic value with the critical value, obtained from the statistical table. You will use table, an appropriate statistical table. Then your step 6 is make decision. What will happen if your computed statistic is less than the tabulated value? Null hypothesis cannot be rejected. So, decision is reject null hypothesis H0 if in this case we are saying t square that computed is greater than that particular tabulated value. You have to see that what is this t square tabulated value. It all depends on the distribution. If it is chi-square, then you have to use the chi-square value here. If it is F distribution, go for F distribution like this. Okay. See this slide. Your first scenario chi-square distribution, and this is the case reject H0 if this quantity is greater than chi-square p alpha. See, already you have computed all those values. In the earlier example, you have computed this value also, you have computed, I think that this value we have not computed, mu 0 is given now. Okay. One of the issue here you must remember that whenever we are talking about sampling distribution of a statistic like this t square is this, we are saying that when null hypothesis is true, this statistic follow this sampling distribution. Please never forget this one. Okay. So, if you change your null hypothesis to something like this, that mu less than mu 0, then you will not get the appropriate distribution because it is not developed. Maybe developed, we do not know. But what we know here that our null hypothesis is mu equal to mu 0, then only this quantity t square, this is chi-square distributed, where t square is this, where sigma inverse is there. So, please do not change your null hypothesis. Actual means there are two hypotheses in this case, null and alternative hypothesis. Null hypothesis is someone which it is a statement which is not yet proven, that hypothesis you were talking about. Okay. There is no actual hypothesis, something like this. It is basically, it is a proposition, you do not know what is the true things, you are trying to prove it based on data analysis. Okay. So, there are two hypotheses, null and alternative hypothesis. In case of population, your scenario 2, your state statistic is this, distribution is this, and reject like this. So, do not look at the equations, you just think the message what I am giving you, that is more important, because whatever given to you, ultimate aim is few things that must be remembered by you. One is what is your random variable. For example, x bar is also a random variable. Then you are creating certain statistic using appropriate statistics using this random variable, this is also a statistic, but for finding out the same distribution you may not get distribution of x bar, you may get distribution of something else. Here x bar distribution is also available, but for computational purpose we are converting into z or t square or something like this. Then you must also know the distribution of this statistic, here it is distribution of t square, and then you have to find out that what are the value, and this is the steps, whether it is t square distribution, z distribution, chi-square distribution, t distribution, all cases things to be followed exactly the same. So, do not forget that these equations may be big, but these equations are no way hampering your understanding. Okay. Then scenario 3, you all know that you will be using the sampling distribution f. So, again your decision will be like this. Now, if this is the case, then see one problem again. Consider example 4, conduct hypothesis testing for population mean vector mu 1 equal to 9 and mu 2 equal to 18, alpha equal to 0.05. See, x bar is given, mu 0 is given. What is your null hypothesis here? Mu 1, mu 2 equal to 9 and 18. Okay. So, you write down this x bar is 10 20, the same problem I am discussing, that mu 0 is 9 18 and s 40 minus 50 100, and this is the calculation. I think you all know that we have already find out that t square is 1.33, 10 minus mu 1 will be mu 10. So, mu 10 square 1.34, 10 minus mu 10, 20 minus mu 20 plus 0.53, 20 minus mu 20 square. What we have found out, that mu 10, this one is your 9, mu 20 we have found out it is your 18. Put into this equation. If you put into this equation, this is 1.33, 10 minus 9 square, 1.34, 10 minus 9 into 20 minus 18 plus 0.53, 20 minus 18 square. You are getting a value 1.33 cross 1 square, that is 1, plus 1.34 into 1 into 2 plus 0.53 into 2 square, that is 4. So, what will be this value? 1.33 plus 2.68 plus 4 into 3 12, 2.12. So, this is 6.13, correct. So, this is what is computed t square computed from data. What is your tabulated value? We say it will follow n minus 1 into p by n minus p, f p n minus p, and you have to find out some alpha value. Alpha is 0.05 like alpha. So, that we have already seen that 19 into 2 by 18, f 2 18, if we write it 0.05, this resultant quantity is 7.51. So, reject yes or accept. Why reject? Huh? You will accept or reject? If t square computed is greater than equal to t square tabulated, then reject H0. So, our computed one is 6.13, is it greater than equal to 7.51? No. So, our decision is fail to reject H0, fail to reject H0. Mu equal to mu 0. No, your null hypothesis H0 mu equal to mu 0. What we are saying then? Suppose I have written 0 like there, basically mu 1 mu 2, that 0 stands for null hypothesis, that is this one is 9 and 18. This is your null hypothesis. What you have? You have x bar equal to 10 and 20, and you have x s, that is what is 40 minus 50 minus 50 and 100. And now you know what is the population characteristics, and based on this t square computed, t square tabulated, both is computed, and you see, if you see this value, what is x bar? 10 20. Now, you are creating one hypothesis, null hypothesis like this, mu 1 0 and mu 2 0, this just to give this 0 notation here 9 and 18. So, 10 minus 1 20 only 1 and 2 that difference, x bar minus mu 0 that difference is 10 minus 9 is 1 and 2. The statistics based on this sample covariance matrix, when you are computing like this, you are not finding out this one is similar to 0 0. Getting me? That difference what you have assumed and coming, there is not much difference. Actually what is required to know here, your chi-square I think we have taken f distribution, this is f value, this is your distribution. When you are taking alpha value is 0.05, this is what we are getting here 7.51 and your value is coming somewhere here 6.13. It is within this interval. You cannot reject the null hypothesis. Okay. Now, what will happen if you go for difference in two population means? Getting me? How do you proceed? You have done in univariate case, yes or no? We say that we want to test the equality of two population means. I think you please remember your univariate case. There are two variables x 1 and x 2 and you computed x 1 bar and x 2 bar. You also computed S 1 and S 2. You may be knowing the sigma 1 and sigma 2 depending on the situation. You have created a random variable which is x 1 bar minus x 2 bar. You recollect your lecture on test of equality of two population mean under univariate situation. This is a random variable. Now, this random variable there will be expected value, that is mu 1 minus mu 2, and there will be variance. You have seen that this is variance x 1 bar plus variance x 2 bar. So, that one we have seen that this is variance means sigma square by n 1 plus sigma 2 square by n 2, where n 1 sample from population 1 and n 2 sample from population 2. What is multivariate counterpart of this? Getting me? What will happen? Your random variable will be a random vector x 1 bar minus x 2 bar. This is a random, your random variable is this variable vector. Yes, and your population is like this. So, what happened, your x 1 bar from the first population, x 2 bar from the second population, again these are all p variable case. Then you have computed S 1, you have computed S 2. What are these things? Covariance matrix for population 1, covariance matrix for population 2, and you know that suppose the first one is n 1 or n 2. Okay. So, I will give different notation, I will give A and B, because I have developed in like this A and B, A and okay. The slide I prepared using A and B notation. I am asking you find out the expected value of x1 bar minus x2 bar, last bench here, that side. Idea? Any idea? What I said? Expected value will be this for univariate case. Multivariate case also will be the same thing, but only vector notation. So, that means expected value of x1 bar minus x2 bar, that is nothing but mu 1 minus mu 2. How many variables are there? There are p variables. So, this will be a quantity like this. Suppose mu 1 1 minus that, I think I will give a, then that will be better. I told you x bar minus this bar, mu a minus mu b, then this is mu a 1 mu b 1, mu a 2 minus mu b 2, like this, mu a p minus mu b p. So, those who are absent in univariate class, for them it is difficult to grasp, and you will never learn, because you have missed the vital issues already. Then what will be the variance part? X a bar minus x b bar, that will be variance of x a bar plus variance of x b bar. I have shown you in multivariate univariate case, variance of this is this. Forget about how this derivation, all those things are coming, because we are not a statistical expert, we are users. So, then if sigma square is the variance for the univariate case, we all have seen that capital sigma is the counterpart in multivariate case. So, if it is A, this will also be A. If this one is B, I will go by this. So, this one will be sigma A by N A, because you have seen earlier that from population around N1 and N2 is divided, I am now denoting by A and B, and this will be your sigma B by N B. Okay. Now, you think what will happen? I want to create Z. What is the approach? Z approach is you first write down the random variable minus its expected value divided by square of its variance. So, I can write down here very clearly what is my random variable x 1 bar minus x 2 bar. So, let us write x 1 bar x a bar minus x b bar minus expected value means mu a minus mu b divided by, you can write down the variance component sigma a by n a plus sigma b by n b. Now, see, this is in the multivariate domain, and you have already seen in univariate case that similar things you have created when I have written like this A transpose x bar minus A transpose mu by that square root of A transpose sigma A by n. This is for only one population case. That means, similar analog has to be created for difference also. Please remember, here is one random variable vector, that is x 1 bar minus x 2 bar. Although you are taking sample from two population, finally you are creating one random variable vector x 1 bar, x a bar and x b bar, x a bar and x b bar. Okay. So, the same principle will be applied now. Only thing is that one more component added by denoting sigma A, sigma B, your later on we will be adding S A, S B, something like this, but essentially other things remain same. So, you have similar situation here. You are sampling from multivariate normal populations with known sigma 1 and sigma 2. You ask some question, otherwise it will be one sided game. You go through this slide first. Is there any problem in understanding the three scenarios?
So the two populations are independent?
Independent. So, scenario 1, scenario 2 and scenario 3, here first one is like this, that sampling from multivariate normal population, known sigma 1, sigma 2, sampling from multivariate normal population with small sample size, unequal, unknown but equal sigma, not unequal, unknown but equal sigma, and sampling from multivariate normal population with large sample size and unknown sigma 1 and sigma 2. We will discuss the second one, because that one you will be using more frequently. Now, in univariate case, again you recall that we said that if sigma 1 square equal to sigma 2 square equal to sigma square, then we have used certain estimate of sigma or sigma square. What is this? We say SP square. Can you remember that we say a square pooled? I think you can remember there we have used that N1 minus 1 S1 plus N2 minus 1 S2 by N1 plus N2 minus 2. Here we will use the same thing. Here what is our case? Sigma A is sigma B equal to sigma. This is our case. We will be creating similar S-pooled covariance matrix, and that will be NA minus 1 SA plus NB minus 1 SB divided by NA plus NB minus 2. Okay. So, that this one is our estimate of sigma. Okay. Now, let us see some of the slides first, and we will explain, and there is the same way that confidence region first, followed by your simultaneous confidence interval, but please understand in totality we are repeating what we have developed so far in univariate your single population, single multivariate population case. We are repeating this one. The random variable is changing. Okay. If you do not understand this, so I am repeating it also several times. I am saying the random variable is changing, accordingly the statistics, that total formulation is changing. Otherwise, the statistic, that the t square statistics, again the A for chi-square distribution, those things remain same. Your change is in terms of computation here. You see this slide and have a feel of it. Small sample case. All those things available in Wichan book, Johnson and Wichan book, but they have used some other notation, not AB. maybe they have used 1 and 2, something like this. What I am saying here, my condition is like this, that you are sampling from multivariate normal population. There are two such populations, X A, N P, mu A and sigma A, X B, that is again N P, mu B, sigma B, and your population covariance matrix, both the matrices are equal to sigma. And your sample statistics is, what is my random variable? X A bar minus X B bar. This minus its expected value, please get the connection, link point. We said the random variable minus its mean expected value. So, expected value of x bar A and minus x bar B, that will be mu A minus mu B. In the single population case, you have used the formula for T square x bar minus mu transpose. Now, no longer you are using x bar, you are using the difference between two population mean vector. So, x A bar minus x B bar, that is similar to x bar, analog to single population, that is x bar minus mean, that transpose. Then followed by what happened, there you have used S inverse, here you have two population case. So, and sigma A equal to sigma B equal to sigma. So, you are calculating the S pooled first. This S pooled is this one by N A plus 1 by N B into S pooled. S pooled is the same equation what you have seen earlier. What is S pooled here? N A minus 1 into S A plus N B minus 1 into S B divided by N A plus N B minus 2. So, you are writing this, and you know that earlier we also derived in univariate case that 1 by N 1 plus 1 by N 2, that quantity will be there. So, this is what is the very covariance part. So, you have to take the inverse of this covariance, then you square this one x A bar minus x B bar, that random variable, that is squaring.
In single population there are around n at the beginning. So n is
Single population?
there was n at the beginning. Then x bar minus
Yes, yes, yes.
but n is
Here n is here.
actually that part is going to
It is coming here N A plus N B, because in earlier case what happened, this is 1 by root n and then n you are taking other side. Variance part in univariate case, what is that? Sigma by root n, scalar quantity, that sigma by root n, that derivation is such that root n is going to the numerator, you are writing. When you are going for hoteling T square, what is happening? They are also single population case, that n is there and coming to the numerator, and you are writing here n. In this case, what is happening? This n is taken care of by 1 by N A plus 1 by N B. See, this n component is coming because of variance. In univariate case, in multivariate case, because of covariance. When it is single population, you do not have any problem, this square n component will come here, and here it is the two population difference case. So, the variability will be taken like this, okay, and this is the quantity. This quantity follows what distribution? F distribution again, okay. But you see some other part, the two component is there. In earlier case, it was n 1 minus n minus 1 into p by n minus p. What it is written here? N A plus N B minus 2 into p divided by N A plus N B minus p minus 1, that you have to remember, okay. Otherwise, if you want to derive it, very difficult, it will go, you will forget that, okay, I will stop reading this multivariate statistics. This one, and see the F P, P is the numerator degrees of freedom, and Na plus Nb minus p minus 1, this is the denominator degrees of freedom, and your confidence region will be t square less than equal to this. We will not repeat this. I hope that you are understanding. I am sure you are understanding. But those who were present earlier, they are understanding. I am sure. Whether you may be, it is maybe sometimes difficult, because so much of these terms mu A, mu B, and Na, Nb, all those things. But the concept, the message must be clear to all those who were attending from the beginning. If not, then please ask me question, come to my room, and again you get it clarified. And those who are not attending, forget. That is the large sample, and in large sample case, Chisquare distribution you will use. This is for the confidence region. Now, this is one example, and it is the data I have just arbitrarily given, but we have done one study in some of the coal mines. This is a real application I am telling you. These data are not from that real application, but similar application we have done. We have found out that the management was facing problem with managing accident, particularly injuries in underground coal mines. They have gathered lot of data, lot of injury data, means people who were injured, and there are another group who were not injured. Our aim was that whether there is difference in characteristics of that two groups. So, we have taken 24 variables, and then we 150 observations each from accident group, from non-accident group. Then that means what is, this is a two group phenomena. I want to test the mean differences between the two population. If there is difference, then we have to find out what are the variables making the difference. That type of study we have done. It is applicable to quality control also. For example, you will find out in Johnson and Johnson one application is given in from the police department activities point of view. That part you please check. So, now suppose this is the case, two population and you are getting x a bar in SA, x b bar, S b like this, and then what you require to do, you first find out the confidence region. Same thing you are doing with more computation, nothing else. So, you are finding out t square, then finding out your what is the your sampling distribution, and you are making this confidence region. Okay. And I ask you to practice, very difficult. If you do not practice, it will be difficult. Multivariate is really complex, but if you go to the theoretical side, then it is, we do not have that background, and but application side, even then it is complex. Although we are in the, now we will use the same situation, maximization lemma and Bonferroni approach. Big equations. Okay, big approach. Okay. Now, see that maximization lemma and Bonferroni approach, the difference is coming chi-square and z. Then your the second one, equal unequal and unknown case, here you are using this F distribution available in Johnson and Wichern, you do not require to write. Third case, large sample chi-square distribution. You create your example here. Next class I will ask you, there is no example, I thought I am giving, but I find that no, it is better do not give anything. Next class you will be giving one example for this. Arbitrarily I will be asking some of you. Then hypothesis testing. Nirmal, should I stop now? Hypothesis next class I will discuss, or it is okay? Okay. So, you want 1 more hour on hypothesis testing, similar. Okay, then I think this is the end today, and next class tomorrow here for all of you.